Hello, my name is Ernest Ryu. I'm an assistant professor of mathematics at UCLA, and this is a re-recording of a talk that I've given in several occasions. The title is Toward a Grand Unified Theory of Accelerations in Optimization and Machine Learning. Let me start by spending a few slides to talk about why it is that I care about this problem. In modern machine learning, one trains a neural network which we denote as f theta. So it's a function parameterized by the parameter theta by solving an optimization problem of this form. So we have the function f of x, the neural network, taken as input a data point xi. Xi is the ith data point, and you can think of x as something like an image or an email. And then there is corresponding labels, yi. So yi is the ith label. And think of yi as containing information as such as whether the image contains a cat or a dog, or whether the email is a spam email or not. The neural network outputs a prediction of what the correct label yi ought to be. And we have a loss function. The loss function evaluates how accurate or inaccurate the prediction is. So if the prediction is incorrect by a large margin, then the loss will output a large value. If it's correct or close to correct, then it will output a 0 or small value. And then we sum over our entire training data set from data set 1 up to data set, the final data point, big N. And then we find a neural network parameter theta such that the neural network makes correct predictions on the training data. And hopefully once that is done, then the neural network will be able to make good predictions on new data that the neural network has not seen during training. Training is an anthropomorphized term. And solving an optimization problem of this form is what training consists of. So this is an optimization problem. So then to solve this problem, we need to use an algorithm. And the algorithm that is commonly used is called stochastic gradient descent, SGD. SGD solves this optimization problem with this simple one-line expression. So to describe what's going on here, this equation describes how we make our update from the theta parameter at iteration k to the parameter at iteration k plus 1. So this describes our update. We take a random data point. So our index ik is a random data set, a random index, randomly chosen from 1 up to n. So think of it as selecting a random element within our data set. We take the x data point, its corresponding label. We evaluate the loss on that particular data, and then we move in a direction that reduces that loss. Here we have this parameter alpha, which is referred to as the learning rate. So what's described here is the vanilla version of SGD. And nearly all modern machine learning setups use either SGD or a variant of SGD to solve the optimization problem. And this process is referred to, again, as training. So I'm an applied mathematician, and as such, I want to understand why and when training works well. However, if we take a very theoretical mathematical lens at this problem, one might conclude that the optimization shouldn't work well. Why so? Well, because the optimization is a non-convex optimization problem, so there can be local minima. Perhaps the training gets stuck at local minima. Or if you can take an alternate route and say, well, the class of training neural networks is an NP-hard problem class, and there is no known efficient way to solve an NP-hard problem, so we shouldn't be able to efficiently solve this training problem. But this classical complexity theory approach clashes with the empirical observation. We all know that deep learning works very well. We all know, we've all seen the remarkable results that come out of deep learning. And of course, in deep learning, the core of deep learning is learning or training. So something about training ought to be working well in the modern deep learning practice. So the theoretical statement that deep learning training ought to be computationally hard, and the empirical observation that deep learning training works very well, there is a mismatch and something's missing. And this is quite troubling. So there's something that we don't understand, but really learning and training, it is the algorithmic foundation of machine learning. And as a theoretician, it's a bit concerning to me that there is this significant part of the algorithmic foundation of modern AI that we do not fully understand. However, trying to understand the entirety of training is perhaps too big of a problem class. So maybe let's try to be a bit more focused. So within training, one algorithm that's commonly considered is SGD with momentum. So if we ignore this term, then this would be plain SGD, where GK is a stochastic gradient. But in SGD with momentum, we have this additional term where beta is usually a positive parameter. And what this means is, in addition to moving in the negative gradient direction, negative stochastic gradient direction, we also have this momentum term where we continue to move in the direction that we've been moving in. Here is a cartoon illustration of the mechanism of momentum. So on the left, we have gradient descent or stochastic gradient descent without momentum. And as you can see, the convergence is slow because we oscillate back and forth. And we eventually do converge to the global minimum, which is the center of these ellipses. But the convergence is slow due to the oscillatory behavior. Whereas on the right, we have a depiction of gradient descent with momentum. And in this case, the convergence is much faster because initially we do the SGD with momentum does exhibit the same oscillatory behavior, but as the iteration progresses, it builds up momentum, and then it just moves towards the minimizer much more quickly. And indeed, momentum is a core component of modern deep learning training. Momentum is used in most of the optimizers, so things like Atom, RMS prop. These are all used widely. And generally, people say that momentum is sometimes, although not always, helpful in training deep neural networks. So the question that I raise is, momentum is said to provide an acceleration, and that's what people say. And what people mean is you turn on momentum and things go faster. But what does that exactly mean, and why is that the case? That's the question I want to ask. And one might think that, well, this illustration kind of gives you the answer, doesn't it? Because, well, yeah, I mean, without gradient descent, you oscillate, and then with gradient descent, you pick up momentum and you move more quickly. Well, but I describe these figures as a cartoon illustration because I don't really think this illustration gives a fundamentally deep understanding of what's actually going on. And let me prove it. So if these figures represent a complete and a rigorous understanding of why momentum is helpful, then it should have some predictive power. Does this intuition have predictive power? Because, as I've just said, momentum sometimes provides acceleration, often provides acceleration, but actually not always. Sometimes you tune your optimizer, you tune SGD with momentum, and then you tune the momentum value. So beta is a tunable hyperparameter that you need to adjust. And sometimes you tune it to zero because without momentum, things are the best. So if this is the correct picture, then are you able to predict when momentum should be useful and when momentum should not be useful? When momentum is not useful, so when beta equals zero is the optimal value in this hyperparameter tuning, can you explain why it is that in that particular case, momentum was not helpful? And I find that I think I understand what people are trying to say with this figure. This is a very common this is a common figure that you can find on the internet. People, sort of repeat the intuition described in this figure commonly when they describe why it is that momentum should be helpful. And I think I understand what people are saying there, but I don't think I don't have the ability. I don't think this intuition gives any predictive power. I am not able to predict when momentum is helpful and when momentum is not helpful. And for that reason, I think this question does not yet have a good, rigorous theoretical answer yet. So then let's be a bit more serious about momentum. Well, in the field of optimization, Nesterov acceleration is the famous use of momentum that provides provable speedup. So let's consider the optimization problem of minimizing the function f of x, where x is an n-dimensional decision variable. And we assume that the function f is convex, and furthermore, we assume that the gradient of f is Lipschitz continuous. Let's first consider the algorithm gradient descent, which is the simplest possible algorithm. So given starting at position xk, the way we move to position xk plus 1 is we evaluate the gradient, and then we move in the negative gradient direction, scaled by a certain amount. Okay. And I'm going to introduce this notation xk plus. So xk plus means at position xk, we will make one step, one will take one gradient step. Gradient descent, again, is a very simple algorithm. It's a very intuitive algorithm. It means it's based on the intuition that you should just go downhill, which makes a lot of sense. And under these set assumptions, we are able to prove a 1 over k convergence rate. So that's good. The function value reduces at a rate 1 over k. However, this rate is famously suboptimal, and it can be accelerated. So Nesterov's celebrated fast gradient method, FGM, has this form. So at position xk, we take the gradient step, but in addition to that, we have this term. Now, these are kind of funny looking coefficients, but for now, just think of these as a positive coefficient. So theta k minus 1 is a positive number, theta k plus 1 is a positive number. So this is a positive momentum coefficient. And we have this thing. So think of this as a momentum term where we continue to move in the direction that we've been moving in. Famously, again, this Nesterov's fast gradient method achieves a 1 over k squared rate, which is faster than the unaccelerated rate 1 over k. The modern use of momentum in deep learning, it originates from Nesterov and Polyak. In convex optimization, we can prove that momentum does indeed provide an acceleration. So here's a theorem. If you use Nesterov's fast gradient method, you get a 1 over k squared rate of convergence, as I stated in the previous slide. Now, how do I prove that? How do we prove that? Well, here's one way to prove it. Okay, so what you do is you define this Lyapunov function. Think of this as like an energy function. Now think of theta k squared as think of this as k squared. Okay, so we define this thing. Here we have this z thing. Now, if you remember, the algorithm never talked about z. So z is a thing that doesn't appear in the algorithm, but we're just going to define this thing nevertheless. We can define things. Once you define these things, then it turns out that this UK sequence is a decreasing sequence, or it's a non-increasing sequence. One would also say that this is a dissipative sequence, like energy. So we can show that the UK sequence is decreasing. And once you do that, then the proof is basically done because again, theta squared is basically k squared. So the fact that k squared times function value, that's less than uk, which is less than u0 because this term is 0 when k is equal to 0, and you just get this. Okay, so once you define this energy function and show that its dissipativity property, then the proof is done. So this is a proof that works, but why does it work? You see, this proof, and if you were to, let's say, open up Nesterov's textbook, there's going to be a slightly different looking proof, but that proof as well, you can open up the proof, read things, and then what you would do is you would first sit down, read the proof, and then try to verify it yourself. And with, say, something like 15 to 30 minutes of focus calculations, you would be able to verify the correctness of these proofs to one's satisfaction. But just because you're able to confirm the correctness of a proof doesn't mean you really understand it. For this proof, for example, like where did this UK definition come from? How did one come up with this? What is this Z thing? Like why this Z thing doesn't appear in the algorithm. Like what is this thing? Why is this supposed to be helpful in the analysis? Well, and that's how I also feel about it. I've personally written many papers in the area of acceleration. Other smart people have worked on acceleration, but the fundamental principle behind acceleration seems to remain a mystery. The algebraic calculations in the existing proofs are certainly verifiable. They're not that complicated, but they are not transparent. And again, it's just not me. It's not just me. There are several other, smart people, respected people in the field that agree that the problem of understanding acceleration is an open problem. And because acceleration is such a major, important component in the theory of optimization, it really is a major open problem in optimization and machine learning theory. However, interesting, there has been a breakthrough in this area. And the breakthrough is that recently several new acceleration mechanisms, other than distinct from Nesterov, have been discovered. So it turns out that acceleration is a much more diverse phenomenon than initially thought to be. Now, at this point, I should perhaps define what I mean by acceleration. So here's an informal definition. So given a setup that yields certain, that admits a simple and relatively intuitive base algorithm, an acceleration is a less intuitive but faster variant of that base algorithm. Now, it's a kind of it's a definition of a kind where I'm basically saying that you know it when you see it. But in this talk, I'm going to show you several accelerations, and I think you will all agree that the ones that I show do indeed constitute accelerations under this definition. So a lot of new accelerations, distinct from Nesterov, have been discovered. So perhaps now that we have a collection instead of just one, perhaps the various acceleration phenomena have a unifying structure. And perhaps finding and characterizing this unifying structure will provide us with a complete understanding of acceleration. Okay, so now let's talk about accelerations in discrete time. I'll show you some examples. So here's a list of accelerated methods, and here I've roughly classified them. So if there's a Nesterov type, there's the anchor type, there's the Kim-Fessler type, and these are all actually quite recent. So the theory of first-order convex optimization is, of course, a very classical field, but most of these algorithms are pretty recent, 2016 or later. And I'll just mention in passing, without going into any details, that the reason we are we are experiencing this spur of discovery in this field is due to the computer-assisted proof methodology called the performance estimation problem, PEP. What the PEP does, it finds a convergence proof of an optimization algorithm by solving a semi-definite program. I'll just leave it at that. So because of the PEP, we're seeing a lot of these new developments. Okay, so in the previous slide, I listed just a bunch of stuff and classified them into the three categories, which I'll talk about in this talk. But also, I just want to mention that there are other accelerations that I do not yet know how to classify. So there's the Anderson acceleration, there's the invisibility detection acceleration, there's the Shambal-Pock-Davis-Jean acceleration. I think these accelerations are distinct from the three classes that I've described in the previous slide, but maybe if I were to think about them more carefully, maybe they fit into them, or maybe they warrant creating another category. I just haven't had the time to think about these in much detail, and maybe I'll do so in my future work. But the point is that the zoo of accelerations is diverse. That's the point that I want to make. And now that we have a diverse zoo of accelerations, as a mathematician, I'm questioning. I want to ask, are they interrelated? They should be. I hope they are. It would be disappointing if we have a collection of these completely unrelated things. I mean, they look different, but they have components that feel related, and I hope they are related in a interesting and useful way. So if they are interrelated, then perhaps could there be a periodic table of accelerations? Maybe there is a standard model of accelerations that imply the existence of new undiscovered accelerations. By studying these phenomena together as a collection, as a zoo, maybe there are insights that we can extract that would otherwise be very difficult to extract if we were to look at one acceleration one at a time. All right, so I've been talking about all these new distinct acceleration phenomena. I'll show you an example. So let's consider the fixed point problem. So here's the fixed point problem. We want to find a fixed point of the operator t. Now, we need to make some assumptions about the operator t. So what we will do is we'll assume that this operator t is 1 over gamma contractive, where gamma is bigger than or equal to 1. So if gamma is equal to 1, then t is actually not strictly contractive. It will be just merely non-expansive. If gamma is strictly larger than 1, then t would be strictly contractive. Given a fixed point problem, the most classical algorithm for finding a fixed point, which goes back to Banach and Picard, is the classical fixed point iteration. So what you do is you have a starting point x0, and then you just repeatedly apply the operator t, and we hope that the iteration converges to a fixed point. The fixed point iteration is used very commonly in a wide range of scientific and engineering problems, and it's been known for a very long time. It's just considered just the standard algorithm for solving the fixed point problem. Surprisingly, however, this classical fixed point iteration is suboptimal, and it can be accelerated. So here's the accelerated algorithm. It's called optimal contractive helper, which we abbreviate to as OC helper, and it's the optimal algorithm. Okay, so let's spend the time to actually read through this algorithm. Okay, so when you're at position yk minus 1, the way you get to position yk is you apply the operator t to the current point. But instead of setting the output of the operator to be the next iterate, what you do is you take a weighted average, a convex combination, a weighted average between the output of this operator and y0, which is the starting point of this iteration. The here is that this phi k parameter. This determines the weights that go into this weighted average. A phi k is defined as in this way. So phi k is an increasing sequence. So so phi k increases. So 1 over phi k decreases. So the weight that goes into mixing in y0, it diminishes as the iterations progress. Okay. Um, so we have this algorithm. How fast does it converge? Well, here we can show that OC Halpern converges at this rate, and you'll just have to trust me that this expression is faster. That this value is smaller than what you get with the standard Banach contraction argument, which is a convergence rate of gamma to the power k. Now, interestingly, this rate yields a convergent rate even when the factor when gamma is equal to 1, when you have a merely non-expansive operator. In particular, when gamma is equal to 1, then this theorem, it guarantees a 1 over n squared rate. And this is faster than the 1 over n rate that you would get with the plain Km fixed point iteration. Okay. Also, I'll just quickly mention that in the field of optimization, there's the notion of complexity lower bounds. Complexity lower bounds establish that algorithms satisfying certain conditions, in this case, the span condition, cannot be faster than the established lower bound. I won't spend, in the interest of time in this talk, I won't spend much time describing the sort of the mechanics of lower bounds, but I'll just state that in this work, we show that OC Halpern is optimal. It cannot be improved because there's a matching complexity lower bound. Okay. Let me show you yet another acceleration mechanism. So let's consider the minimax optimization problem. So there is a loss function L, which is a function of x and y. And in this minimax optimization problem, we minimize with respect to x and we maximize with respect to y. We need to make some assumptions on the loss function L. So we will assume that L is a convex concave function, meaning it's a convex function of x when y is fixed, and it is a concave function of y when x is fixed. The gradient of L, so we assume that L is differentiable, and we assume that the gradient of L is a Lipschitz continuous function. A solution in a convex concave minimax optimization problem is defined as a saddle point. So we say x star comma y star is a saddle point, is a solution if unilaterally changing x will only serve to increase the loss value, which is undesirable because what we want to minimize with respect to x. And then unilaterally changing y will only serve to decrease the loss value, which is undesirable because we want to maximize with respect to y. To put it differently, a solution is defined as a pure Nash equilibrium. Let's define the saddle operator G. G is basically the gradient of L, but we have the gradient of L, and then the negative gradient, so we have the gradient of L with respect to x, and the negative gradient of L with respect to y. So we flip the sign on the y variable. We do so because with x we want to minimize, but with y we want to maximize. So by putting a negative sign here, that reflects the difference. That reflects the sign difference in our objective. Also, if we put the minus sign here, then that makes G what's called a monotone operator. So that's another reason why we do this. It can be shown due to convex concavity that a certain point is a saddle point is a solution if and only if the output of this G operator is equal to 0. Okay, so then how do you solve this minimax optimization problem? So one might think, let's just do basically gradient descent. So the analog of gradient descent, which is referred to in this case as simultaneous gradient descent ascent, has this form. So the zk, given a position zk, we get to the next iterate zk plus 1 by moving in the negative alpha g direction. This algorithm, however, in general does not converge. There's a simple counterexample for which this diverges. So then what is the convergent baseline algorithm? The convergent algorithm is called the extra gradient method. So the extra gradient method is classical algorithm due to Korpelovich in 1976. And it looks like this. So let's read the algorithm. So what we do is, here I have this diagram. So starting at zk, now what we do is evaluate the g operator, and we move in the negative g direction to get to zk plus 1/2. And then at zk plus 1/2, we evaluate the g operator, but instead of moving in the negative g direction from there, we go back to our starting point zk, and now move in the negative g direction, but with the g evaluated at zk plus 1/2, and that takes us to zk plus 1. Okay, so this is a classical algorithm. Its convergence behavior is well known. So here's yes, and the gradient magnitude, it reduces, it goes down at rate 1 over k, and this is well known. But this is suboptimal, and this can be improved. So the accelerated minimax optimization algorithm is called extra anchored gradient. So the algorithm looks like this, and let's read through it. So starting at position zk, what we do is if we evaluate the g operator, we move in the negative g direction, and then we apply this term. And this term is something that I refer to as the anchor term, and we've seen something similar in the OC-Halpern algorithm as well. This term serves to pull the iterates back towards the starting point. The initial point is z0 by a certain amount. And the strength of the anchor is given by this anchor coefficient 1 over k plus 2. And well, this diminishes as the iteration progresses. So at zk, we move in the negative g direction, and then we have the anchor pull us back to z0. That takes us to zk plus 1/2. And then at zk plus 1/2, we evaluate the g operator again. And then we go back to zk. We move in the negative g direction with the g evaluated at the intermediate point zk plus 1/2, and then we have the anchor pull us back towards z0 with this anchor of strength 1 over k plus 2, and that is our next point is zk plus 1. So yeah, so this is an accelerated algorithm, and EAG exhibits a 1 over k squared rate, which is faster than the prior rate of 1 over k. And there's a complexity lower bound for EAG, and its EAG is up to constant optimal. Okay, so next, let me show you yet another acceleration. So now we're going to go back to the problem of performing convex minimization. So we want to minimize a convex function f of x. Again, we assume f of x is convex, and its gradient mapping is Lipschitz continuous as before. However, different from before, what we'll do is we'll measure suboptimality by the gradient magnitude rather than the function value suboptimality. Now, because this is a convex optimization problem, if the gradient is equal to 0, then the function value suboptimality is equal to 0. In other words, this being 0 is equivalent to this being 0. However, this measure being small is not equivalent to this measure being small. Okay, so what are the then performances of the existing algorithms? Well, if you just apply plain gradient descent, then gradient descent gives a 1 over k squared a decrease on the squared gradient magnitude. And Nesterov's accelerated fast gradient method exhibits a 1 over k cube guarantee. So that's nice. But then what's the complexity lower bound? What's the optimal rate? Well, the classical lower bound established by Nemirovsky, it achieves a 1 over k quad rate. And there's a gap between k cube and k quad. So, okay. So then the question is, what is the optimal accelerated rate for making gradients of convex functions small? Well, the acceleration, the optimal rate is achieved by what I refer to as Kim-Fessler acceleration, because it's of course due to Kim and Fessler. The algorithm itself is called OGMG, and it looks like this. And this algorithm it very much resembles Nesterov's acceleration. But so here we have the gradient term, and then this term is the momentum term, this basically the same kind of momentum term as Nesterov's acceleration, except that we have a different kind of momentum coefficient. So here again, think of this momentum coefficient as just some positive number, but the numbers, the values are different. And I'll get to the specific values of these momentum coefficients at a later point in this slide. And then this OGMG compared to Nesterov's acceleration has this additional, what I call correction term. It's, in my mind, this correction term is less important. In any case, OGMG, it exhibits a 1 over k squared rate, and it's accelerated. But wait, I just said that 1 over k quad is the lower bound, and here we have 1 over k squared. So what's going on? Well, here's how you get the optimal rate. So the way you get the 1 over k quad rate is through what I refer to as a concatenation mechanism. So what we'll do is we'll concatenate Nesterov's fast gradient method and Kim-Fessler's OGMG. Here's the strategy. We take a starting point and we execute k iterations of Nesterov's fast gradient method, and Nesterov's fast gradient method will return an output. So we take that output, and then we feed that into the Kim-Fessler OGMG as the starting point, and then we run k additional iterations. So we run 2k iterations in total. Now, this concatenated method will exhibit a 1 over k quad convergence rate. Now, why is that the case? Well, Nesterov's fast gradient method, of which we run k iterations of, it provides a 1 over k squared guarantee on the function value suboptimality on the output. OGMG, which we execute k iterations of, it requires an initial suboptimality on the function and produces a guarantee on the squared gradient magnitude. Now, because the terminal guarantee of Nesterov's fast gradient method and OGMG, and the initial requirement of OGMG, because they match, because they're compatible, you can concatenate them. And if you put them together, what will happen is the concatenated method will have a rate that is 1 over k quad, which is 1 over k squared times 1 over k squared. And we get a terminal guarantee on the squared gradient magnitude. Okay, so I've talked about these three acceleration mechanisms that are distinct from Nesterov. And at the beginning of the previous section, I gave you this classification: Nesterov type, anchor type, Kim-Fessler type. But actually, how did I make this classification? Well, my criterion was to classify accelerations based on their continuous time models. So in this section, I'll talk about the continuous time models of these different acceleration phenomena. And the reason I do this, as opposed to just talking about discrete algorithms, is because continuous time models are simpler and easier to analyze, and they reveal more easily reveal certain structure of the algorithms. So let's start with Nesterov. So Nesterov acceleration in continuous time looks like this. So we again consider the problem of minimizing f of x, where f is convex. So if we take a Nesterov type algorithm, so perhaps Nesterov's fast gradient method, and we consider the limit in small step sizes, the limiting dynamics satisfies this second order ODE. Now, if you think about this ODE, imagine there is the symbol m is here, and m has value 1. So we can think of this as describing a particle of mass 1. So this is m times acceleration. It's subject to a potential F. So F is a potential, and then the gradient of F is the force exerted by the potential. And then the particle also exhibits friction. And the friction, interestingly, has a time-dependent friction coefficient. The friction changes as a function of time, and the coefficient is 3 over t. So at time 0, the friction is infinite, and then for positive time, you have a finite time-varying friction coefficient. Okay, so interesting. And in continuous time, we can do a continuous time analysis of the convergence rate. So the way you do this is you define this energy function u as a function of time. So it's t squared, a function value suboptimality, times this thing, whatever it is, just you can define it. And then if you compute du dt, you can show that that's less than or equal to 0 through direct calculations. So now that we've shown that this U energy is dissipative, then our proof is basically done, because t squared times function value suboptimality is less than U. and then ut is less than u0, and at u0 we have this. So then we divide both sides by t squared, and that yields a 1 over t squared rate. So that's how you do the analysis in continuous time, and it tracks how you do the analysis in discrete time, but this is simpler to think about than the discrete time counterpart. What about these acceleration mechanisms that use the anchor? Well, okay. So for the Minimax optimization problem, we had this G operator. Let's just rename that as an A operator. And then for the fixed point problem, what we can do is we can take this fixed point operator T and then do this transformation, which I won't spend the time going into details, but that will give us, we're able to extract the corresponding A operator from that. And this A operator is, crucially, it's a monotone operator. So once you do that, then we can find out that for the minimax optimization and for the fixed point problem, the continuous time model is the same. And the continuous time model looks like this. So this is a differential inclusion. Now, if you're not familiar with the notion of differential inclusions, then you can just mentally replace this inclusion symbol with an equality and everything will just be fine. So x dot is equal to minus a. So a, you should think of this as something similar to a gradient. So x dot equals to minus gradient. So that resembles very much gradient flow. But in addition, we have this anchor term. So again, this anchor term serves to pull the dynamics back towards the starting point x0, and the strength of the anchor diminishes at rate 1 over t. How do you do the analysis here? Well, what you do is you define this energy function, which is, well, it's funky. It starts as 0 at time t. And then you can show, because t squared times t, so this energy is 0 at time t. And then what you do is you compute du dt, and then you show that that's less than 0 by direct calculation. So the energy starts at time 0. It starts at 0, and then it's decreasing. So this is always a negative energy. And then what you can do is you take this additional step based on using the Young's inequality, which is something that I would be able to explain in, let's say, 5 minutes of explanation. But in the interest of time, I'll just skip it. And we were able to conclude a 1 over t squared rate for this setup that matches the 1 over k squared rate of discrete time. So the point is, I've skipped over the 5-minute explanation of the applications of Young's inequality, but the point is, it's a much more simpler argument that you can make in continuous time to intuit about where the 1 over t squared rate comes from. Okay, so then what about Kim-Fessler? Well, again, let's consider the problem of minimizing the function f of x, but now we're going to measure suboptimality by the gradient magnitude. Now, if we take OGMG, a Kim-Fessler acceleration method, and consider the limit of small step sizes, we get this ODE, where, well, this is interesting. So it's an initial value problem where there's an initial position, initial velocity, which is 0, and then the terminal time is big T, and at terminal time, this friction coefficient it blows up. Now, from a mathematical perspective, it's not a priori obvious that this is a well-posed ODE, whether this ODE admits a good solution between the interval of 0 and big T, but that's not a priori obvious, but that's something that can be proved. And this is really interesting because this friction term is time reversed compared to the Nesterov ODE. Now, compared to the Nesterov ODE, there's a factor 2 here, but that's kind of immaterial. That's not that important. The important thing is this friction term, which is time reversed. So that's well, okay, that's noteworthy. In any case, how do you do the analysis in continuous time? Well, you define this funky Lyapunov function. You show that it's dissipated through direct calculation. And then at terminal time, we have these terms that all blow up. But what you can do is you can use L'Hopital's rule to conclude the 1 over t squared rate, the accelerated rate. Okay, so I've introduced to you some new acceleration phenomena distinct from Nesterov, and then I introduced to you their continuous time models. And by looking at these continuous time models, hopefully you're convinced that these are genuinely distinct phenomena. They're not sort of the same thing, just masked, disguised. They really are different phenomena. But the title of this talk is a grand unified theory of accelerations, and the whole premise is that I want to find connections between these different acceleration phenomena. So let me tell you about two things that I've done to make connections between these different and interesting acceleration phenomena. So the first thing that I've done is motivated by this simple experiment. So first, let's first look at this experiment first. So what this is here I'm solving a convex minimization problem where this dotted is a two-dimensional convex minimization problem, and this dotted line denotes the set of solutions. So this is an optimization problem where the solution is not unique. And here I'm going to use Nesterov's acceleration with slightly different momentum like coefficient parameters. So these are like the same kind of accelerated methods, but with slightly different parameters. We see that if we start all these methods at the same point, they will start at the same point, and then but as the iteration progresses, the trajectories diverge, and they eventually converge to different solutions. And that's fine because for these accelerated methods, there was the guarantee that we would converge to a solution at an accelerated rate, which they do, but there was never any guarantee that they should converge to the same point. So it's fine, but that's their behavior. But let's contrast that with the anchor type accelerated methods. So we're running these methods on the same convex minimization problem, but here are four algorithms. FEG, that's a FEG, APS, EAG, those are Minimax algorithms. OHM is a fixed point problem algorithm. In any case, you start at the same point, and as you can see, initially, because these are different algorithms, the iterates diverge. But very soon, within a few iterations, the trajectories merge and they become essentially indistinguishable from each other. And they merge at a rate that's much faster than the rate of convergence. They merge much more earlier than they converge to the same point. So this motivates the definition of merging paths. So if we have two algorithms producing two sequences, we say, I'm just going to say that the algorithms have merging paths if the iterates get close to each other very quickly. So and this is a way to make that quantitative. And here is a theorem that we've shown. So these four algorithms, EAG, FEG, APS, OHM, these are all have merging paths with respect to each other. Now, the merging path property provides a very strong notion of equivalence. So because the paths all merge very quickly, if you have a convergence rate on one of the equivalent algorithms within the family, that implies the same rate on the entire family. So that's very nice. And also, conceptually, this establishes a formal equivalence between accelerated algorithms for different problem classes. So EAG, FEG, APS these are minimax optimization algorithms, and what we've shown is that these algorithms are equivalent in the sense of merging paths to a OHM, which is a fixed point, which is an algorithm for a fixed point problem. So to me, this gives me an understanding that although these two problem classes, minimax optimization and fixed point problems, are different, they're of course related, but they're different. Their optimal accelerated algorithms are equivalent in this specific sense. Okay, let me tell you about something else. Now, remember when we were talking about the continuous time models, this was Nesterov's continuous time model, and this was Kim-Fessler's continuous time model, where I just dropped the factor of 2 because it's not that important. We have this glaring symmetry. Now, this glaring symmetry, it cannot possibly be a coincidence. Could it? There ought to be some underlying deep reason where that explains this kind of symmetry. At least as a mathematician, that's what you hope for. So we spent a lot of time trying to think about how to understand this, and here's how we think we should understand it. So for these continuous time models, instead of describing the dynamics with a second order ODE, we can describe them using what's called a first order integral differential equation. So x dot is given by the integral of the previous gradients. So x dot at time t is the integral from 0 to t of all the previous gradients. So the direction that we should move in, it's a weighted combination of all the previous gradients, and how we put in the weights, that's given by this H kernel, this kernel matrix H, kernel function H. Okay, so then with this representation, the Nesterov acceleration accelerated ODE can be described with is corresponds to this kernel, and then Kim-Fessler corresponds to this kernel. And as you can see, there is a certain degree of symmetry here. And this can be actually done exactly the same way in discrete time. So in discrete time, the way we have a what's called an H matrix representation, where given the position xk, the way we get to the next position xk plus one is we move in a direction. This is our movement, and the movement is given by a combination of all the gradients that we've evaluated that we've seen so far. And the way we combine the previous gradients is given by this h values. And if you put together all these numerical values of h's, then you can put them in a matrix. So I'm going to refer to this as a H matrix. OGM, which is a Nesterov type accelerated method, has this particular H matrix representation. The formula looks kind of messy and or complicated, and that's fine. You don't have to pay attention to the specific form, but the point is that we know exactly what this H matrix looks like. Now, OGMG, which is a Kim-Fessler type acceleration, we have been able to figure out what the H matrix representation looks like. And interestingly, it's the antidiagonal transpose of this matrix. Okay, so let me explain. Given a matrix, right? So you have a diagonal direction, but there's also the another diagonal direction of a matrix. Now that other diagonal direction is called the antidiagonal of a matrix. Now, if you flip the matrix along the diagonal direction, you refer to that as taking the transpose. If you flip the matrix along the antidiagonal direction, you refer to that as the antidiagonal transpose. It turns out that the H matrix representation of Kim-Fessler and the H matrix representation of Nesterov, they are antidiagonal transposes of each other. Okay, so that's a very interesting sort of symmetry that we see. And our main result that underpins our H-duality theorem is as follows. So let f be a convex function, and then the gradient is Lipschitz continuous. So these are all the standard assumptions, and we're going to consider the discrete time setting. And the following are equivalent. So if we have a matrix, if we have a method represented by a certain H matrix, and we are able to establish a certain rate on the function value using a certain energy function argument, so there's a certain asterisk here, but if we are able to establish a guarantee on the function value, let's take that method and let's flip it. We take the anti-diagonal transpose, and we will refer to that as the H-dual method. The H-dual method then will have a guarantee, the same bound on the squared gradient magnitude, and vice versa. So this is our duality theorem. This is a duality result on the optimization. This is a duality result on the optimization algorithms. And the Nesterov acceleration and the Kim-Fessler accelerations are dual accelerations in this sense of H-duality, and in the sense that the bound of one type directly translates to the bound of another type. So maybe to put it differently, Kim and Fessler, instead of publishing their result, they could have resorted to this kind of argument where they take a Nesterov acceleration and they flip it to get their convergence guarantee, their acceleration mechanism. Or alternatively, we could imagine, Nesterov, like some time machine thing where Nesterov didn't invent his Nesterov acceleration, but Kim-Fessler did invent theirs. Then we could take Kim-Fessler's acceleration, we flip it, and we would get Nesterov's acceleration. Okay, so let me conclude. We have a diverse zoo of accelerations, and there's some interesting progress towards systematically classifying and relating them. And the figure that's shown here is it's a description. It sort of illustrates my sort of mental model of the state of affairs. So Nesterov acceleration and Kim-Fessler acceleration, they are related by H-duality. So I have this dotted box surrounding them. So they're not the same, but they are duals of each other. And then for anchor acceleration, we have this, I drew the box with a more solid line, a thicker line, because we have this strong characterization through the merging path property, in particular relating the anchor acceleration for Minimax, the anchor acceleration for fixed point problems. They're all equivalent in a strong sense through this merging path property. And then there are these other things, infeasibility detection, Anderson acceleration, CPDY acceleration. Those are other things that I hope to get to at some point. Okay, so yeah, so a grand unified theory of accelerations seems a bit distant, and I guess from the title of this talk, if you're expecting for me to tell you about a grand unified theory, I apologize that I don't have it yet. And indeed, from the results that I've shown you, the conclusion that one would have to draw is that a grand unified theory is still distant. But I argue that it is a grand unified theory is a feasible and productive goal to pursue. And through pursuing it, perhaps maybe we can solve the open problem of understanding acceleration. Thank you.